Okay, so today we are going to solve this problem, and it's an important problem. Okay, first, so we have the governing equation. Okay, it's the following. We have del squared w prime plus L squared w prime equals to 0. And L squared is defined as the n squared over u squared minus ugg divided by u. And that's we call the, so that gives us the L we call scalar parameter. Scalar parameter, okay. And so we can write in other way, like d squared w prime, dx squared plus d squared w prime, dg squared plus L squared, okay, w prime equals 0. Okay, so we are going to look at a special case. Okay, so assume, okay, u g is equal to 0. Okay, so we or ug is constant. That means you can have you assume win shear is 0 or ug is constant. Let's probably just assume ug equals 0. Okay, so that means u is constant. Okay, so we call it uniform flow. And just normally we call it uniform flow. That means we don't have wind shear. Okay, so then that makes it constant. That makes L squared will be equals to n squared equals to u squared. Okay, and of course L will be equals to positive and negative, or negative n over u, right? But assuming n is constant, okay, it's positive. Okay, that's normally the case. N is positive, and u, assuming it's from west to east, that's x direction. So u will be positive. So then that gives us, okay, L equals to n over u. Okay, assume u is is positive. That means it's okay from west to east. Then that is in x direction, so it's positive. Okay, and if you are interested in easterly flow, no problem. You can just easily make the argument. That shouldn't be that a problem. So L will be like this. So then the equation reduced to the following: d squared w prime dx squared plus d squared w prime dg squared plus L squared w prime equals 0. Okay, where L squared is equals to n squared equals to u squared. Okay, which is equals to constant. That's important because the problem we're solving without constant, then you have to be careful because, and to a certain point, we still can assume it's non-constant. Okay, we can still get the solution. But after a certain point, you have to assume it's constant, okay, in order to solve the linear, to solve the differential equation. Okay, so now this is the governing equation. Okay, now, second thing is, we assume we are sinusoidal mountain. Okay, so the mountain, we assume, maybe I probably just say low boundary condition. Okay, so now we have low boundary, so low boundary condition. Okay, that is 30 prime equals to u partial h partial x. Okay, at g equals to 0. Okay, and for h of x equals to hm times sine kx. Okay, then this gives us the lower boundary condition of 30 prime equals to u, okay, and then times partial x of hm sine kx. Okay, so I go quickly because we have already discussed yesterday. So then you bring hm out, and the partial x of sine kx will be k times cosine kx. So this gives us 30 prime equals to u hm and k and then cosine kx. Okay, so this is the lower boundary condition at g equals to 0. Okay, so we have this governing equation, and the lower boundary condition like this. Okay, third, can you see it? Maybe I better put over there. The third is upper boundary condition. Okay, because we need two boundary conditions to determine the solution. Okay, and it's a second order differential equation. So we need two boundary conditions to completely solve the problem. So upper boundary condition, then it depends, okay, on flow regimes. Okay, we'll discuss this detail later on. And okay, we have two regimes. One is flow over the mountain. That's just like pure gradient waves. We have vertically propagating wave regime. Okay, that has different upper boundary condition from that okay, kind of evolution flow. Okay, so we have this. Okay, don't worry about this. We have come to this point. Okay, we'll explain it. So now we have the governing equation, and then we have low boundary conditions. Okay, which different from before. Before we just have the flat terrain, and now we have the sinusoidal mountain. We have the forcing. Okay, for this particular problem, and then third thing is upper boundary condition, which depends on flow regimes. Okay, so now we are ready to solve, right? Okay, so we have this this one and this one. Okay, so now try to solve it. Okay, okay, now we try to solve it. So we assume, okay, the solution is okay, is also sinusoidal. Okay. Okay, so we assume that then W prime could be cosine kx plus sine kx. And then you have the coefficient here. And since horizontally we decided to be sinusoidal, okay, and then this is k, this x, right? So now we have W1 of g and plus W2 of g, okay, right? Because we're cosine, we're sine. And then in vertical direction, we have different solutions for sine and cosine solutions. Okay, so this will complete Of course, you can also use 1 or 1, but you'll find out it's not complete solution. And to a certain point, you probably cannot even solve it. If you can solve it, you're lucky, but you only get the partial solution, okay? So now, if we have this, we substitute W prime into this governing equation, which is, I believe, this governing equation is, we call it 5.1.5. Okay, 5.1. So we substitute it into 5.1.5. Okay, so 5.1.5, we have d square, dx square. Okay, and then we have the W1 cosine kx plus W2 sine kx. Right, that's first term. And then am right? That's correct, right? And then we have W2. We have d square, dg square of W1 cosine kx plus W2 sine kx. Okay. And then plus we have L square. L square. Okay. Remember, L square now is equals to n square over u square, which is a constant. Okay. So L square times W. Okay. Then we have W prime. That's W1 cosine kx plus W2 sine kx. Okay. And that equals to 0. Okay, can people see it clearly if I write here? Yeah? Can they? Or it's better to be on that side? It's okay, huh? No? It's okay. Okay, so now we can solve this, right? So now we have d square W1. Oh, no. Because this is on x. W1 is functional g only. Functional g only. So we pull the W1 out. And then d square, dx square of cosine kx. What's that? Will be, first time will become k, negative k sine kx. And the second time, we pull k out, okay, and then become negative k square cosine kx. Okay, so this one, this will give us, first time will give us k sine kx negative, right? First time, first differentiation, ddx. And second time, d square dx square. Take one more time, we keep k. Okay, so let me see. So second time, d square dx square. You take one more time of this. So you keep negative, right? And k, you one more k. So you have k square, and then you have cosine kx. So then we have negative k square, and then cosine kx. That's first term. And second term, okay, it's similar, except it's sine kx. So you pull one k out. Next time you pull negative k out. So you have negative k square, same thing. So you have negative k square, but we have W2, and then sine kx. Okay, so that's first term. And second term, it's easy. Why? Because the only dependency on G is W1 and W2. Okay, cosine kx, sine kx, you can just pull out because it's independent of G. Okay, so that's become easy. So then plus, okay, we have the W1, dg square, and then cosine kx. Right. And the second one will be the square here, W2. Remember, W1 and W2 are functions of G only. And then we have this dg square times sine kx. Okay, that's this term, this term. And now plus the last term, we just split. So then plus L square, and then W1 times cosine kx. It's pretty easy, we just copy down. Okay, move this into there. Then we got L square, W2, and then sine kx. And the whole thing have to be equals to 0. Okay, so I'm going to move to that side. Okay, I assume everybody got this down, right? Right? Yes? Okay, then we have this. Okay, and that we have the solution like to the left-hand side there. So here we have cosine terms. We have sine terms times sine terms. Okay, so we can combine them together. Okay, combine the same cosine terms together and same sine terms together. So then we have with the cosine term, like this one, cosine term. We pour them together. Okay, so that gives us partial W1 partial G square. Okay. When you say partial G, you can say partial, or you can say round, okay, and round, okay. Some people say that, okay. So we have partial square, W1, partial G square. That's, okay, first term. And then minus K square, and then W1, right? And then plus L square, W1. This together with cosine kx. We just connect them, pour them together like this. And then, okay, those sine terms, we also pour them together. So that gives us plus, okay, d square, W2, dg square, minus k square, W1, W2, sorry about that, plus L square, W2, and then sine kx. Okay, since sine and cosine functions are, we call orthogonal, okay, they cannot be equal to 0 simultaneously. Okay, then these two individually have to be equal to 0 because they are orthogonal. Okay, so this means, okay, we have d square, W1, dg square, plus L square minus k square, W1. I just pour these two together, equals to 0. And also d square W1 dg square plus L square minus K square W2 equals 0. Okay. So if you don't believe it, you can substitute, okay, the W1 into here, then you get it, okay? It's, okay, consistent. We just more or less this become negative K square and bring it here and change this W prime to be W1 over W2. Okay, so we have this solution. Okay, now, okay, so probably next thing is here we have L square compared to K square like before in pure grid waves. It depends on your solution. Okay, depends on your regime. So say let's assume case 1. Okay, so assume case 1. We have say L square is less than K square. Okay, because the solution is different from L square greater than K square. So let's assume this case 1 is like this. And this means which kind of flow regime? Evanescent. Okay, flow. Okay, so this gives us evanescent flow. Okay, because when L square less than K square, this gives us L less than K, and L is N over U, K is 2 pi over L, okay, 2 pi L, okay, that's wave number, right? Wave number 2 pi divided by L. L is wavelength, like this. So this means we have L divided by U less than 2 pi over N, right? I just, okay, swap this, 2 pi divided by N, and then multiply L, then become like this. So, okay, you should know the answer now. Okay, so what is physical meaning of L divided by U? It's the observation time, right? So as I guess we are done with this, so I can write here. Okay, now, so, okay, we are sinusoidal mountain, and this is L from mountain peak to mountain peak. Okay, this is called same phase, or from valley to valley. That's okay. Or you can have any point. That's called a phase of a wave to here to here, okay, or here upslope to upslope, okay. Anywhere goes to same phase to same phase. That's L. So L, and then we have U. So L divided by U. That's okay. Air parcel are directed to here. That's a time. Okay. We call the observation time. Okay, for air parcel 2, okay, pass through one wavelength, horizontal, like this. And 2 pi over N, N is per second. So 2 pi over N will be second, right? That's a time. That's a time period for vertical oscillation. That's called buoyancy oscillation. Okay, that's this. So this is the buoyancy oscillation period. Okay, here. Okay, that is vertical oscillation. Okay, and this is more horizontal observation. Okay, so now what we have now is we have Lu compared to 2 pi over n, which one is larger? Which one is larger? This one is larger. Yeah, so larger. Okay, that means the time it takes to pass over the mountain wavelength, one wavelength, it takes less time compared to vertical oscillation. So in other words, when you try to oscillate it, the air pass already passed through the mountain. So you don't get much chance to do vertical oscillation. So you don't get wave energy kind of being propagated vertically. Okay, so this will give us the evanescent flow. Okay, because vertical oscillation takes a longer time. Okay, if on the other extreme, other case is if the mountain is much wider, it takes longer time to pass over, the air passer will get chance to oscillate, and that will get chance to, pump, kind of push the air on top and bottom to have vertical oscillation, and then you got the chance to propagate the wave energy vertically. Okay, so now we are in this case. Okay, we're in this case. So then, I guess we are done with this. Okay, so then we can rewrite the solution like the following. Okay, W1 GG. Okay, I just write it in a different way. Minus k squared minus L squared. Because our k squared is larger than L squared, so we write this way. Then this is positive, and then W1 equals to 0, and then W2 GG minus k squared minus L squared, and W2 equals 0. Okay, so now that's a good thing we learned from chapter 4, the pure graded waves, because we got the solutions already, a general solution. And then once you got general solution, then in this particular case, only one thing different is we have no boundary conditions, different from before. Okay, we have, so up to this point is same as before. Okay. Okay, so now I guess everybody got this, right? Okay, now so like this. Okay, so now the solution of this is the solutions. Okay, because we have two parts. Solution will be W1 equals to what? Equals to what? Say here, it's second order differentiation. So we have A, say 1, and then what's this? E to the, so let's probably define it as lambda, as lambda. So this will be E to the lambda G plus, A2, right? A2 E to the minus lambda G. Huh? Yeah, right. Yeah, lambda is equals to, lambda square. Yeah, that's good. Yeah, okay. So lambda is equals to square root of k squared minus L squared. Okay, thanks. Okay, so then we have this, right? And then for second one, so the first one like this. Second one is W2 equals to what? We say P1. A1. Oh, sorry. We have P1, right? P1 here. And here we say A2, right? A2. Make sure, okay, can you check my, okay, oh, we can check quickly. E to the lambda g plus P2, e to the minus lambda g. Let me check to see if my symbols are consistent so you don't get confused. Okay, so we look at regime 1, okay, the evanescent flow. Okay, so I call it regime 1 here. Regime 1. It's case 1, okay, same thing, regime 1. So then, okay, we discussed about this already. Okay, oh, here, okay, here, give you a hint, okay. If somebody asks you verbally or on test, okay, and give you a value like, oh, okay, if I have U equals to 10 meters per second, if my flow is 10 meters per second, and N is 0.01 per second, then people ask you, what will be the wavelength of the mountain, okay, in order to be in regime 1. Then you can calculate it. You can calculate it. Okay, you can calculate it because you can base on this. Okay, you can base on this. Okay, so say if N is equals to 0.01 per second. Okay, and so say U is 0.01. Oh, sorry, 10 meters per second. 10 meters per second. Okay. Then if somebody asks you, okay, the flow, if the flow that, okay, flow is evanescent. If flow is evanescent, okay, how wide the mountain, the sinusoid mountain, should be. Okay. Then what you can do is you can let L over U equals to 2 pi over N. Okay, and then your L supposed to be equals to, you're supposed to have this, right? Like this. So your L supposed to be less than 2 pi times U divided by N. Then you can roughly estimate. Okay, then this is 6.28 times 10 divided by 0.01. That gives us 6280 meter. That's 6.28 kilometers. So your mountain has to be less than 6.8 kilometers. Okay. In other words, your mountain is supposed to be narrower. Okay. Narrower. Okay. So if air parcel will go over quickly and doesn't get chance to do vertical oscillation too much. Okay. So this type of thing you could be asked in the exam. Okay. So now we have this, and let me see. I wanted to check the symbol. So, okay. So now, okay. A1, B1. Okay. So I'm okay. So now, this is a solution. Okay. So now, no matter it is W1 or W2, we have two coefficients, A1, A2, B1, A2, B2. And what will determine what factors are going to be used to determine A1, A2, B1, B2 is boundary conditions. Very good. Okay. Okay, so now let's start with maybe upper boundary condition. Okay, so apply the upper boundary condition. Okay, we have lower or upper. Okay, we can decide. You can apply lower boundary condition first if you want. Okay, but if you apply upper boundary conditions, okay, in this case it's easier because you knock out. Okay, you knock out one term. Okay, make a simpler solution. So now, if we want to apply the upper boundary condition, so now this term, including this term too, they have the disturbance by the mountain, right? Disturbance, and this disturbance is going to grow with height. It's going to grow with height exponentially. So that's unphysical because your disturbance here. Okay, and disturbance will be less and less, okay, compared to far away. So this is kind of not physical. And this one is we choose this one because we call this is the solution is bounded. Okay, it's unphysical. You have disturbance here, and then keep growing to far infinity. That's impossible. Of course, you can have disturbance when it's unstable. Here is stable case. Okay, when unstable, it can grow with time, but you still have more disturbance nearby compared to far away. Okay. Okay, so this is called the boundedness. Okay, upper boundary condition. Okay, so then that means we'll knock out these two terms and make it easier. Okay, so now solution becomes W1 equals to B1 e to the minus lambda g, and then W2 equals to B2 e to the minus lambda g. Okay, so that's good because we knock out one coefficient. So we only have one more coefficient to determine. That's B1 and B2. And they are going to determine by lower boundary condition. Very good. Okay, lower boundary condition. Okay, so now I guess maybe let's try to write this side and try to use the board for explanation. So people, of the campus can see board clearly. Okay, so now I assume we already have this. We already this. Okay, so I can erase that. Okay, this is regime 1. We have this. Okay. Okay, so now for W1, okay, that's equals to B1 e to the minus lambda g. Okay, so and remember, okay, we have W prime of xg equals to W1 head of g, right? And then what? And then cosine kx plus W2. Okay, I think we just use this W2 or g and then sine kx. Remember, that's in the beginning we assume the solution, okay, includes cosine and sine terms. That's what we have. Okay, now we already got W1, right? W2, we can substitute back there. So that means W prime xg equals to this is P1 e to the minus lambda g cosine kx plus P2, okay, e to the minus lambda g, and then sine kx. Okay, we just substitute. Okay, we just substitute this into 30 prime. Okay, then we get this. This we assume this, and then we solve for W1 and W2, and then become like this. And then to decide P1 and P2, we will apply the low boundary condition. Right? Everybody clear? Okay, so now, agree? Okay, so now we have this 30 prime, because this, okay, and this is low boundary condition here, okay, this is low boundary condition here, okay, low boundary condition here. Okay, so in order to apply low boundary condition, we have to let g equal to 0. Okay, so at g equals to 0, then 30 prime of x 0. Okay, let's finish this before break. Okay, and this will give us what? E to the 0 is equals to 1. Okay, so then this reduces to P1 cosine kx plus P2 sine kx. This one has to be equals to this. Okay, so these two has to be equal. So this 2 has to be equal. Okay, these 2 equal. So when they are equal, that means we are going to have, and we no longer need this. Okay, we no longer need this. That means, okay, P1 cosine kx plus P2 sine kx must be equal to UHM k times cosine kx. Right? So again, cosine and sine functions are orthogonal. Okay. In the equation, you just have to divide them, okay, and each equal to 0. So this means we have P1 minus UHM times k cosine x kx plus P2 sine kx. So they are orthogonal. So individual one has to be equal to 0. This one has to be equal to 0. P2 has to be equal to 0. Okay. And this means P2 is equal to 0 and P1. So this implies P2 is equal to 0. P1 is equal to UHM times K. Okay. Okay, now I think we are done with this. Okay, so now this means this is our solution. This is our solution. Okay, and only thing we need is P1 and P2. But through the applying of low boundary conditions, we found P2 is equal to 0, P1 is equal to this. So we can substitute this into here. That gives us a solution. The prime of xg equals to P1, that's UHM times k, and then e to the negative lambda g. Okay, and then cosine kx. And P2 is 0, so this term is gone. So this is our solution. Okay, so this is a good place to stop and take a break of 10 minutes. Okay, thanks. Okay, so let's continue the discussion. So now we got the solution. Third prime, xg equals to u hm k e to the mass lambda g minus lambda g. Okay, and then cosine of kx. And sometimes it's useful. Most of the time it's useful, W prime, but sometimes we can define other parameter, other variable related to W prime, which make us easier to visualize the solution. Okay, where W is up and down, but other parameter, okay, variable related to W is if we can define a vertical displacement, okay, which is related to W prime. Then we can see it because we can see, oh, at this point, okay, the air parcel is going up how much and going down how much instead of velocity. Okay, so if we have both solutions, it will help us to, okay, see the dynamics. So that will be helpful. So if we define the vertical displacement, okay, eta, okay, like this. What's this? Airplane? Okay, what's that? What's that? You never see that? You have never seen that? That is what I learned in mathematics, okay, because I major in math. So that's called the such that, okay. So such that, okay. And I think you can ask your friends if they major in math, okay. They should know this symbol, okay. Okay, so such that third prime is equals to the eta dt. Okay, so say if you have mountain here, okay, and here at a certain height, say g1, then this one will give you the perturbation, okay, how much it is from the undisturbed level. So say g1 is 5 kilometers. So say for example, and then eta will give us, oh, at this point is up, is up, is up, but at this point it's down, 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 down. So then, okay, so this is eta. Okay, remember we have this shallow water flow, like this. We have shallow water. Let me see. We have shallow water like and we have the undisturbed upstream, far upstream height is capital H. Remember that? Okay, and this water surface, this water depth, and this water surface, and this is, we call H, right? H prime. Remember that? That's called vertical displacement from the undisturbed level. Okay, this is called water surface perturbation. Okay, so same as that. So if we define this way, and what's this in steady state and two-dimensional flow? Because this will be partial eta, partial t, right? Plus u, partial eta, partial x, okay, and plus v, partial eta, partial y, but this is, okay, two-dimensional, okay, because 2D, and this is gone, because steady state. Then that reduced to 30 prime equals to u partial eta partial x. Okay. Can you see clearly on this side? Yeah? So when we have that, that means the eta dx will be equals to 1 over u, the 30 prime, okay, from negative infinity to a certain point x, okay, and then dx, okay, yeah, we just do vertical integration of this, okay, times dx, okay, like this. So, sorry about that. I think I have to do this. Maybe I jump the gun too much. So this gives us the eta dx equals to 1 over u 30 prime. Okay, and then we have partial eta, partial x dx from negative to x equals to 1 over u, negative infinity to x 30 prime dx. Okay, then that will give us, this will give us eta. So that gives us eta equals to this. So we have this. Okay. Okay, now once you have that, then we can substitute our solution. We can substitute our solution into it. That is this one. Substitute into here and take integration. Okay. And that gives us, okay, we substitute this, and that gives us the following: eta equals to 1 over u. Okay, this is simple manipulation, but this new variable is going to give us very, very good way to visualize, okay, the flow, the solution. And so then we have u hm times k, and then e to the minus lambda g, and then cosine kx, and then dx. Okay. Okay, now u can pull out, cancel out, and then hm and k. K is constant. We only treat one constant. Okay, it's normal mode. Okay, it's not a Fourier transform. So this becomes, we have hm times k, and then this is function of height, not x. Okay, so we can pull out to, this is x here, negative infinity, cosine kx dx. And that gives us the following. Okay, what's the integration of cosine kx? Sine kx over k. Okay, so this is sine kx over k. Right. So then k cancel out. So we got hm, and then e to the minus lambda x, and then sine kx. Is this correct? Supposed to be g. Okay, so now we have another solution in terms of the vertical displacement eta. So now we have eta of xg equals to hm e to the minus lambda g cosine, sine kx. So we said when you have mountain, the flow comes in, it's going to be forced and then follow the mountain. Okay, follow the mountain. Okay, now you can see it clearly from eta. Okay, so at g equals to 0, then eta of xg equals 0 is h naught e to the 0 is 1. Right? It's sine kx. That's wonderful because, okay, we assume that. And now we can see it. From W, we cannot see it. Okay, of course, you can always work it out. But from eta, you can see it that this is just mountain at 0. Yeah, this is a mountain, right? Okay, we assume, remember, we assume the h of x, the mountain, the topography is like this. Terrain is equals to hm sine kx. So at g equals 0, eta, the displacement is just follow the mountain. Okay, beautiful. And then, okay, then you can, as I mentioned earlier, you can, when you have sinusoidal mountain like this, okay, so at eta of x and 0 will be just follow the mountain. And you can plot, this is like a streamline. You can plot it, streamline. Okay, at a certain point, like, okay, G1, then you can plot the perturbation, okay, from G1. That's eta 1. You can plot it. And so you can see the whole picture. You can see the whole picture like that. So that helps you to visualize. Like, okay, of course you can always manipulate, interpret the flow field from W prime. You can always do that. Okay, but with eta, that helps you to visualize it. Because if you have this, okay, this is G1, right? G1, just like water surface plus displacement up and down, then you can see flow like this and then compare to the mountain. Then you can clearly see it. Okay, and that's what we did in the lecture note. Okay, everybody done with that? Okay, that's what we can see here. We can see here. So now you can plot it like upper one. That's the solution for the current regime, evolution flow. You can plot it. Okay, you can plot it. So you can plot the result. Okay, using eta, you can plot it. You can plot it. Okay, and you let me see on point A. Okay, and now let's look at W prime. Because for eta, so for eta, this is just simply, okay, at surface, it just follow the, at g equals 0, just follow terrain. And then above, it's also sinusoidal, also sine function, but you just decrease the height, the perturbation. So just exponentially decaying like this. Okay, that's called evanescent flow because the oil amplitude is going to diminish, decreases with height exponentially. See here. So the solution still sinusoidal, but with amplitude, wave amplitude at higher level decreases exponentially. Okay, that's all. That's our solution. It's pretty easy to. Okay, now what's this? Okay, this means, okay, for W, this means at G equals 0, that's surface. Okay, then W prime is equals to U, HM, K, and then cosine KX. Right, KX. So this means we have mountain like this. Okay, this mountain is, so this mountain is sine kx hm. And this is the mountain h equals like this. Okay, this mountain at surface. And for eta, it's going to just follow the mountain like this. How about 30 prime? Okay, so this sine function, and this is x. So say if this point is x equals to 0, then sine 0 will be 0, right? And what will be the x here? This will be 90 degrees, right? 90 degrees, sine function becomes 0. So what's 90 degrees? It's pi over 2. Okay, so this had to be equals to pi over 2. That means kx is going to be pi over 2 divided by k. So this is pi over 2k. Okay, and oh, sorry, this is supposed to be, sorry, this is 90 degrees. Okay, 90 degrees, that's pi over 2. Okay, so this will be pi over 2k. And this will be what? Pi over k. Right? And here will be 2 pi divided by k. Okay, right? So then, okay, now that's the mountain. Okay, what do we have here? Okay, this kx is equals to 2 pi to 0 is 0 at this point, and you can have pi over 2, okay, and then that's 90 degrees, that's here, okay, or maybe easier, I just say kx here, then easier for you to see. Let's just use kx here, then that's easier. Then this will be 2 pi, okay, and this will be pi. This is 90 degrees, this is pi, and what's this? 2/3 pi, right? 2/3 pi. So 2/3 pi. Okay, or 2/3 pi, okay? 2/3 pi, right? So then we have this mountain. Okay, now at x equals 0, what's W? What's 0? At 0, 0. This is 0 point at 0 at height. What's that? Cosine 0. That's 1. Okay, so that's U, HM, K. Okay, and 30 prime at pi over 2, again at g equals 0. This is x, this is g. Okay, so that would be what? At pi over 2, 0. What does that mean? That means at x equals 0, you have upward motion. You have upward motion. And at mountain peak, that's pi over 2, you have 0, no vertical motion. And here, you have downward motion. And here, you have 0, no vertical motion. Okay, so here, W equals to 0. Okay, W prime is maximum actually, maximum here. And W prime is minimum because it's downward motion. Does that make sense? It is. Why? Because it is upslope. Okay, so you've got maximum W. To here, okay, use up, just like you climb a mountain, use up your energy. Oh, I don't want to move anymore. Okay, no motion. Okay, W prime is equal to 0 at mountain top. And then downslope, okay, it's a minimum. It's maximum in downward sense. Okay, maximum downward motion, that is minimum. Okay, so you have this. So flow go like this, 0, go down like this. Okay, and 0 here, go down like this. So this is only horizontal motion here. No vertical motion. Okay, minimum or maximum downward motion, maximum upward motion here. Okay, that makes sense, right? Yeah. And then on top will be just same pattern, except the mountain, the OF is going to be same phase, but decaying. Okay, decaying. Okay, like this, like figure 1A. Okay. Okay. So. Okay, now. So we can visually see eta, the vertical displacement. And now we check W prime. Okay, but besides eta and W prime, we are also interested in other variables like, oh, what's your propagation horizontal wind? That's U prime. And what is P prime? What is theta prime? Okay, you can get them, all of them. Okay, so. Okay, now, okay, so now we can visualize those and make sense. And then what happens to U prime, P prime, and theta prime? We like to know, okay? And you can get them too, okay? Why? Because from the momentum equation, okay, that is we have partial U prime, partial T, partial U prime, partial X, and then we have no rotation, mass Fv prime equals to negative 1 over rho dp dx. Okay, so steady state. Okay, this one keep. Okay, it's non-rotating. That's what we assume our flow is non-rotating. The Earth rotation effect is very small, and this is because of steady state. Okay, and then this will be equals to rho naught. Okay, because of we assume Boussinesq. So the density is constant, okay, everywhere, in every term, except in the buoyancy term, that is in vertical motion, okay, the vertical momentum equation, okay, so, and this reduced to U, partial U prime, partial X, equals to negative 1 over rho naught, dp prime dx, like that, Okay, p prime here. Okay, that's okay. The momentum equation, the horizontal momentum equation. How about the vertical momentum equation? Okay. Oh, let's probably work out. Let's probably work out the continuity equation first. What's continuity equation? Partial e prime, partial x plus partial 30 prime, partial g equals 0. Okay, this is easier. Okay, so because then we have partial u, partial x equals to negative partial 30 prime, partial g. But we have 30 prime. Okay, so we can just take partial derivative of 30 prime. That's this one. Okay, we just substitute into it u hm k e to the minus lambda g cosine kx. Okay, that gives us the following. Okay, ddg, that's the only term gives us changes. The others are constant with respect to g. So that gives us u hm k cosine kx. And then we're negative here. And then times ddg of e to the minus lambda g. Okay. Like this. This will give us what? Partial g of this e to the minus lambda g. That's negative lambda times e to the minus lambda g. Okay, so negative cancel out. That gives us lambda u hm k lambda. Okay, and then e to the minus lambda g, or we can just copy down cosine kx and then e to the minus lambda g. Okay, that's du prime dx. Once you have du prime dx, we can take integration with respect to x. Okay, so u prime will be equals to negative infinity to x u hm k lambda cosine kx e to the minus lambda g and then dx. Okay, so u prime equals to those are all constants, okay, except cosine kx. So we can have u hm times k times lambda, and then e to the minus lambda g, and integration negative for infinity, not assume no disturbance, and then of course it's a kind of approximation. Okay, time to the x here, and then we have cosine kx dx. So what's cosine kx? The integration of cosine kx is 1 over k sine kx, right? So this gives us 1 over k sine kx. K will cancel out, so we'll give u prime equals to u hm times lambda e to the minus lambda g, and then sine kx. Okay. Okay, now this is u prime. This is u prime. This is u prime. Okay, now let's check it. At g equals 0, u prime is equals to what? Very simple, right? Right, because this equals to 1. And the rest the same. So we have u hm times lambda sine kx. Okay. Okay, so this is u prime at the surface. So when kx is equal to 0, this is supposed to be 0. Okay, kx equal to 0. So at kx equal to 0, what is u prime? Kx equal to 0. Sine 0 to 0. So here, okay, here u prime perpetuation is 0. And how about here? How about k pi over 2, 90 degrees? Kx equals to 90 degrees. That's 1, maximum. So you have maximum w, u prime, maximum. Because you have no vertical motion. Okay, this is just like this. When you see that, that is like, imagine you have the mountain like this, and then you have same shape, right? Like this. At top here, just imagine this is just like water pipe. The water pipe here is narrowed down, by which effect it's going to speed up. Bernoulli effect. Just like water pipe, right? Okay, we squeeze and that will speed up. Okay. When I try to teach the mountain wave theory and dynamics, okay, atmospheric dynamics, I kind of mentioned to my students, well, maybe what we learned can be applied to the kind of traffic flow, okay. But too bad, some traffic flow has different property, because when you have narrow road, okay, you don't speed up. It would be great if the traffic flow has Bernoulli effect, okay. So then you want to speed up, okay, you have bottleneck. That's called bottleneck, pinching. Okay. You have pinching, then you can have flow speed up. Too bad we don't. Okay, but here, okay, here you speed up, you slow down. Here it's widen up. Okay, then u prime will be somewhat slower. So okay, this speed up, just like water pipe. Okay, that's Bernoulli effect. Okay, so makes sense, right? And here, speed up. Here, okay, minimum. Let me see. Yeah, here it would be minimum because it's okay. It's negative. It's negative. Okay. Yeah. So now, okay, you have u prime positive, u prime negative. Okay, see here, water pipe, widen up, slow down, squeezed, narrow press, speed up. Okay. Okay, so we are done with this. That makes sense, right? Okay, now, so we are done with this. Okay, let's go back to the horizontal momentum equation like this. This, okay. So this can be simplified. Why? Because we have partial x, partial x. Okay, so what you do is you take integration u, the u prime, dx with respect to x. and go from negative for infinity to x, okay, to x here. Okay, for sinusoidal flow, you probably cannot use negative infinity. I just kind of make it simple. Okay, you probably assume a certain point, maybe which you have 0 point here. Okay, and then that will give you 0. Okay, and now, so this will give us u of u prime equals to negative 1 over rho and p prime rho naught. Okay. So p prime is equals to negative rho naught u times u prime. So this means p prime would be proportional to negative u prime. What's that effect? What's that effect? You have higher wind, you have low pressure. Bernoulli effect. Okay. So higher wind will have this, okay, narrow down, speed up, okay, higher wind will have low pressure. See here, low pressure. Here, widen up, flow slow down, that means U prime. U prime is perturbation, not total wind, okay, U prime is perturbation, okay. So when U prime is negative, that means when U prime is negative, that means the total U is equals to U plus U prime. Still, our negative is smaller than this U. Okay, so still flow in same direction, but slow down. So slow down here. So when you slow down, that means slow down. That means P prime will be positive. That means increase pressure. So you have pressure here. So see here, no pressure. When you slow down, you speed up, slow down, U prime negative. Okay, so your U prime, if this is negative, then U will be less than U, right? Because subtract something. So you slow down. Okay, still in same direction. So then you got high pressure, you got low pressure. Okay, and actually you can just write it out, because P prime is equals to negative rho naught times U prime. So you can have negative rho naught, okay, times U, and we have one U here, so U square, and that's it. Okay, and then Hm lambda e to the minus lambda g, and then sine kx. Okay, so from P prime, you can identify the places, okay, has higher pressure or low pressure, okay, and that's related to the U prime. How about theta prime? We only have one left, theta prime. What's the theta prime? That will come from which equation? We used up, okay, we combine 4 equations into W prime, and then we solve it, and then we define eta, so then we can visualize the streamline, okay, and then we apply continuity equation to get U prime based on solution of W prime, and then we look at horizontal momentum equation that also give us P prime related to U prime, U prime is related to W prime, so we get P prime. Okay, there's only one equation left, that's thermodynamic energy equation. Okay, so we can apply that too. Okay. So what's the thermodynamic equation? That's d theta dt equals to q. Okay. If I have some coefficient there, okay, I just write it a simple way. Okay. But this is going to be 0 anyway. Why? We assume adiabatic flow. We assume that. Okay, so adiabatic flow. No latent heating or surface heating or cooling. Okay, so it's 0. And what's this? This is partial theta, partial t plus u, theta prime, d theta prime, dx plus w prime, d theta naught, dg equals to 0. Okay, so maybe I use theta bar. Okay, theta bar here. Okay, the theta bar, dg, what's that? That's is equals to g over theta bar, the theta bar, dg, and then theta bar divided by g. Okay, here we can use not because of Bojinsk. Okay, you can do that. No, I just multiply by g over theta naught, and then times theta naught divided by g, because this guy is equals to 1, right? So I just do that. Okay, I just multiply 1 and this like this. So what's this? N squared. Okay, so that means we have the theta prime dt plus u times the theta prime dx. And then we keep w prime, and this one becomes n squared theta naught divided by g. Yeah, that's correct, right? And times w prime equals to 0. One term is 0. This is 0 because of steady state. So then we have u d theta prime dx plus n squared theta naught divided by g times w prime equals 0. Let's finish this. Okay, just a couple of minutes. Okay, actually the time is pretty good. Just 2 or 3 minutes, kind of dragged. Then we have solution of w prime. We can base on this solution to find out solution is theta prime. Okay, so this means the theta prime dx equals to negative n squared naught divided by u times g w prime. Right, and then we can take integration. Negative to x d theta prime dx equals to negative n squared theta naught u g w prime dx. Okay, so we have dx here equals to negative. This will give us simply theta prime. Okay, and so only thing we need to do, I think we are done with this. Okay, so this gives us theta prime equals to negative n squared theta naught u times g, and then integration of negative to x. And w prime is here, u hm k e to the minus lambda g, and then cosine kx dx. Okay, we can pull this out. Okay, that gives us negative n squared theta naught, and u cancel out, Okay, we have G here, and then we have HM times K e to the minus lambda G 20 to X, and then cosine Kx dx. Okay, this is pretty simple, right? What's this? 1 over K, sine Kx. Okay, so K will cancel out, right? This is 1 over K, and then sine Kx, sine of Kx. So K cancel out, it gives us negative n squared theta naught over G and HM, and then e to the minus lambda G, and then sine Kx. So this is theta prime. So then we have theta prime here equals to negative n squared theta naught HM divided by G times e to the minus lambda G and sine Kx. Okay. Negative lambda G will just decrease the disturbance vertically. Okay, but with same phase. That means same pattern. Okay, you keep same pattern. Okay, but just decrease with height. So let's examine the disturbance in theta prime. That will give us Ohm region, core region. Okay, due to adiabatic motion. So for theta prime at G equals 0, then theta prime is equals to, this becomes 1, negative n squared times theta naught times HM divided by G. Okay, this guy is a constant. Okay, and then sine Kx. So basically, theta prime will be proportional to negative sine Kx. Okay, now this is Kx equals 0. So sine is 0. Okay, so your theta prime is 0. And here, pi over 2 is 1. Maximum, so theta prime will be negative, right? Will be negative. So negative means it's Ohm region or core region? Core region. So here we have core region here. We're on top of the core. And here we have negative 1. That means we have minimum theta prime. So what does that mean, minimum theta prime? That means Ohm region, right? So we have the Ohm region here. So does that make sense? Your core, your Ohm, maximum, okay, Ohm region, maximum core region, coldest, warmest region. Does that make sense? Yeah, right. Why? Because we have air parcel lift up to the mountain peak. It's expanding, right? And become colder, right? Denser, okay, and then sink down, then to the valley, it's going to be higher pressure, the environment, so get squeezed. The air parcel gets squeezed, and then the molecules bump into each other more frequently because of the mean free path of the molecules are shorter, so they bump into each other. So if we squeeze you guys into that corner, you don't feel comfortable. Okay, why? Oh, okay, too hot. Okay, too hot, too close. Okay, human beings are funny, right? If distance from other people is too short, you don't feel comfortable because you kind of bump into each other. You try to talk about other things no privacy. And when you make it huge, okay, and then disperse people, oh, who are my friends? Okay, I have no friends. If I want to talk to my friends, I have to yell to them. Okay, so, okay, the air parcel is like that. Okay, so then that is the most, okay, warmest region, like this here. So that makes sense. So now we have the whole solution, just based on very simple, okay, some simple idealized situation, steady state, two-dimensional, non-rotating, Boussinesq, okay, adiabatic, okay, all those assumptions, and then that gives us a solution. And that solution gives us, okay, W prime, and then we define eta, so we can visually see the, okay, the flow structure or the streamline, and then based on the continuity equation, okay, W prime will give us U prime, and then based on the horizontal momentum equation, okay, then we got Bernoulli effects, P prime proportional to negative U prime, okay, and then based on the thermodynamic energy equation, okay, and W prime, that gives us theta prime. So we can determine where you are going to have warm region, cold region. Okay, so then that's it for this case. And next thing is, even under the same one, we'll try to study some okay, kind of energy and the momentum fluxes. Okay, so we'll continue this afternoon. Okay, thanks. Okay, thank you very much. So now let's continue what we discussed this morning. Okay, so just a summary. Once we get W prime, then we can define eta, and then eta will be equals to U partial, W will be equals to partial eta partial X times U. Okay, and then that will help us to visualize the streamline, okay, airflow following that eta line. And then we can also get U prime from the continuity equation, and P prime from U prime. Okay, so P prime can be calculated from U prime based on continuity equation, continuity. And then theta prime can be derived from W prime, okay, based on the thermodynamic diagram, thermodynamic energy equation. Okay, so it's summarized in words. Is the maximum and minima of U prime, P prime, and theta prime are also denoted in 5.1a. So the coldest air is produced at the mountain peak due to adiabatic cooling. Okay, like this. Okay, coldest air is produced over the mountain peak. Also, the fastest flow are produced at top of the mountain, and also the low pressure, okay, are produced there. And W, this warmest region is produced as a valley, okay, coldest on the peak, okay, and then minimum wind is produced as a valley, okay. Okay, so now we got the whole picture. Next thing I want to say a few words is about, okay, you look at the picture there, there's no pressure difference exists between the upslope and downslope. See here? You look at here. So here, between upslope and downslope, you don't have the pressure difference. Okay, so here, there's no pressure difference. Okay, so you know why? Because here, upslope and downslope, your pressure is the same. Okay, you have high pressure here, you have low pressure here. So here is, okay, about in the middle. In the middle, high pressure, low pressure, that means your pressure perturbation is 0 there. And then here also is 0 here on the downslope. That means there's no pressure drag on the mountain surface. So we have like high pressure here, low pressure here, right? And high pressure here. And here is pressure perturbation is equal to 0, pressure perturbation equal to 0. So they are same. So there's no pressure difference. That means air upstream is not pushing on the mountain surface. It just go up and go down. Okay, so no drag. And actually you can calculate the drag. How do you calculate it? We can base on this equation to calculate it. Okay, so but there's no net with drag on the mountains. That's what we call mountain drag. And mountain drag can be computed either from the horizontal pressure force on the mountain over wavelength. Okay, like this. Okay, so drag, mountain drag on the mountain surface will be, you integrate from negative pi over k to pi over k. That's one wavelength. Okay, one wavelength because we have pi over k minus pi over k. That's equals to pi over k. Okay, and okay, that is equals to x. So that means kx is equals to 2 pi. Okay, that's one wavelength, 2 pi, from 0 to 2 pi. And so then, how do you calculate? You calculate p prime, okay, at the surface, and times dh, dx, okay, equals times dx. So what does this mean? This means if say, okay, let me just draw, okay, let me see like this. Like this. So say if we look at this part, just look at this part, okay. Upslope, downslope, we want to see the pressure difference. So what's the drag? Drag means this. If we idealize this mountain like this, like a calculus, like this. Okay. Then along this, you have pressure acting on this. This part you don't. This part you don't. Okay. This part you have. This part you have. So then you add it up. Okay. Pressure with the height here. P times dh. So this is okay equals to P prime dh. dh, P times, okay, so P1, dh1, or say delta h1, and then P2, delta h2, P3, delta h3. So then you have summation of P1, delta h1, okay, and then you have I, okay, I from 1 to infinity. Then you take limit of delta h to 0. That will give us integration of P dh. Okay. And then if your delta h is become smaller, then that will approach the real mountain shape. Okay. So that will give us, okay, the P and then dh, dx, and then dx. Okay. And that's called the, actually it's pressure force. Okay, pressure force times this, okay, how much you have, how depth you have, and that give us drag, we call mountain drag. Okay, so now if you do this, okay, you do this on what we have, okay, in our solution, then you find it's 0. Okay, so you can actually do it. Maybe I should let you do it. Okay, yeah, okay, yeah, this will be homework problem. You forgot to email me yesterday about what I said in the class. Yeah, okay, yeah, this will be a a problem.
You mentioned at this time.
Yeah. Okay. So email me all those. Yeah, too. Yeah. Okay. So they can calculate it. So when you calculate it, you have some feeling about it, and you have deeper understanding. Okay. This is just like if you go to a new place, like a city, you go to a new city, and then you live there, and then you don't have a car. Okay. And every time you go somewhere, you always have a friend take a ride here, there. You don't know exactly the city look like. Okay. But if you drive, then you know, or you biking, you do biking, then you know the place. Okay. So you have to do practice by yourself. Okay. We already have the P prime here. Okay. And then the HDX, you can calculate it. You plug in, you can calculate D. Pressure drag. Okay. Wet drag. That's called the mountain drag. And the key point here is for every initial flow, pressure here is identical to here. So there's no pressure force on the slope. Okay. And another way you can calculate the drag is by calculating the vertical flux of the horizontal momentum. It's also called momentum flux, and that is D equals to, rho naught K, and then U prime times W prime dx. Okay, and based on the Elias and Pohm theory, that's equation 4.4.10. It's in the, I think we have that, 4.4.10. Do we have that? 4.4.10. Maybe we don't, okay. But it's probably from the book. Maybe we didn't discuss about 4.4.10. Okay, 4.4.10 is like this. Actually it's there. It's there, actually. It's here. It's here. Yeah. This 4.4 is like this. Okay. It's P prime, W prime. You take integration over one wavelength. Okay. And take average, actually. Equals to negative rho naught times U, and U prime W prime bar, take average. It's called Elias and Pohm theory. Elias and Pohm. Okay, theorem. You know, maybe what I should do is, I think we didn't discuss it in chapter 4, or chapter 4, yeah, we didn't discuss. Maybe what I should do is maybe I upload my book chapters for relevant chapters. Okay, so remind me about that so I can post it, so you can download the book chapters. Yeah, just reference you can download. Okay, it's not in the lecture note, but after lecture note, I put a kind of like chapter 1. You can download it. I can upload chapter 2, 3, 4, and 5. Okay, so you can download it, and then you have more reference. Okay, just in case I refer to some equations, then you can look at that. Okay, that chapter 4 in 2007. Okay, so this is called the momentum flux. Okay, the vertical flux or the horizontal momentum. Okay, oh yeah, I have it here, 4.4.10. Okay, I have here. Okay, so now that's about it for L squared less than K squared, except, okay, we also have the extreme case, which I probably don't have to talk about because I think I already talked about maybe 3 times already. So extreme case is when we have L squared much less than K squared. Then we have the N over U much less than K, or NA or NL divided by U much less than 2 pi. Okay, A is like L here. That's the horizontal width of the mountain. For sinusoidal, that is L. Okay. Okay, L is 2 pi over K. Okay, for sinusoidal mountain. Okay, so this is extreme case. That means what? Means the buoyancy force is much smaller than the advection. Okay, so in other words, your advection over the mountain or over the one wavelength is so small. Okay, the time it takes to go over the mountain is so short. Then the air parcel doesn't get enough chance to do vertical oscillation, which don't give you a chance to disturb the air above and below to oscillate, to make production of wave energy to propagate vertically. Okay, and this is called evidence in the flow. But this extreme case is even worse because it just go over almost like the water flow over the mountain. You don't have the certification effect. Okay, this N is so small. Okay, buoyancy force is so small. Okay, compared to initial force, that is advection. And that gives us this potential flow or irrotation flow. We already discussed this, okay, before. This is nothing new. This is just like we had before, okay. So to summarize it, it's like we did earlier. So to summarize it, it's we have this del squared W prime plus L squared W prime equals 0. And L squared, in general, it is equals to N squared over U squared minus UGG over U. Okay. And in this case, that is d squared W prime, dx squared plus d squared W prime, dg squared, plus if we ignore this, okay, then it will become N squared over U squared times W prime equals 0. So this term is reflecting the buoyancy effect. Okay. And so this term is much smaller than this, almost 0. So the flow becomes d squared W prime, dx squared, d squared W prime, dg squared. Just like you don't have the certification. Density in that fluid is constant. Okay, then you reduce this, and then we call it, okay, or d squared W prime equals 0. We call potential flow or irrotational flow. Or Does anybody know why we call this kind of flow irrotational? Vorticity is 0. Remember, I said this term is is related to the vorticity production, and that is 0. So there's no wave vorticity generated, Okay, so if you don't understand what I just said, go back to earlier. When in the beginning I discussed about actually this equation, and then there's other term with UGG. And then each term has its physical meaning. I say that is vorticity equation. So go back to that and review. If you have a question, you can ask me. Now, so that's about it for this regime. And now regime 2, that's other case, regime 2, that is vertically propagating wave regime. So now you understand this, then it will be easier to understand this, because the mathematical solution is very similar, except just like we had the low boundary. Everybody got this? Yeah. So the regime 2. Vertically propagating wave. Remember our equation was the square W prime, the S square plus the square W prime, the G square, and then plus L square W prime equals 0. And we assume uniform flow, so L square is equals to N square over U square. So this is constant. For this, for what we discussed in regime 1 and 2, we assume this is constant. And then we assume we have low boundary. Low boundary, is we have W prime equals to U dH dx at G equals to 0. And we also assume H is equals to HM times sine Kx. And then we assume the solution is in this sinusoidal form. So W prime is equals to W1, and then cosine Kx plus W2 sine Kx. Remember that? And then we substitute this into there. We produce 2 solutions, and that gives us W1 d square dg square plus L square minus K square W1 equals to 0, and then d square W2 dg square plus L square minus K square W2 equals to 0. So once we solve W1 and W2, we substitute in here, then we get the solution. And so then after that, we assume like regime 1 is L square less than K square. So then we swap this becomes negative, negative, we solve it. So now regime 2 is L square is greater than k squared. That means this term will be positive. This will be positive. And then we have a different kind of solution. Okay. So now this will give us 31 of what? Then we have A1, B1, right? We have A1 of G, okay, and then E to G, okay, we did this equals to lambda, okay, or M. We probably use a different. We can use a different symbol. I don't know what I use. Okay, there, just to M, right? M, right? Okay, so I use M here, square. So this is M square. So then we have this set of equations will become, okay, WGG plus M square W equals to 0, and this is 1, this is 1. And then W2 GG plus M square W2 equals to 0. Okay, and then this becomes very simple equation because it's a second order differential equation with constant coefficients. Okay, and that, okay, we know the solution. Okay, you can go back to the differential equation class you take and then review it. You should be able to find pretty easy answer. So W1 will be equals to A1, okay, E to the I mg, because this is function of height only, okay, and then plus B1 e to the minus I mg, okay, and then W2 equals to A2 e to the I mg plus B2 e to the minus I mg, okay, and then again A1, B1, A2, B2, okay, are going to be determined by boundary conditions, okay, lower boundary and upper boundary conditions, okay. So here we only have one layer, okay, only one layer. Okay, so you can prove this term represent upward propagating wave, this term downward propagating wave, upward propagating wave, downward propagating wave. Okay, yeah, you can kind of, what you can do is probably based on the, okay, vertical flux of the horizontal momentum, okay, and you can calculate that, and you can find that term IMG, positive IMG, represent upward propagating wave, and negative IMG is downward. So you can do that in the wave number space, or in general, if your wave is arbitrary, you can make it equals to a series of summation of the different wave length of the waves, and so your k will be different values, and that is Fourier space. It's Fourier transform, then you can calculate it. Okay, so now we have this, right? M square equals to L square minus K square, and this is just like these two equations. And we are looking for solutions in the form of W I is equals to 1 or 2. Okay, so we have W1 equals to A1 times, oh, we have sine or cosine. Okay, so same thing too. Okay, this probably follow that note. Okay, you can use this one too. In general, you can have this kind of solution. But since we are using cosine and sine for the mountain, so we can do this. We can do this. Okay, so here we can just follow this way. Okay, each year you can do this too. Okay, you just have I, and you have to cancel I out. You have to drop I. So we can use the sine mg plus p1 cosine mg. So when you draw this way, you don't know which one is upward, downward, because they are combined. They're combined. Yeah. Okay. So this A2 sine mg plus p2 and then cosine mg. Okay, now those are solutions. Okay. And so if we substitute these two equations, solutions, into 5.1.12, okay, and what's 5.1.12? I think we probably have here already, okay, so it's probably here, okay, here. Okay, here is 5.1.12, I believe. Okay, right, correct, right. So this is earlier, this, okay, remember here we assume sine or cosine in x direction, and then W1, W2 can be solved from here, eventually get this. Okay, so we still don't know A1, A2, B1, B2 yet, because they are going to be determined by the boundary conditions, okay, which once we substitute in, then we can apply boundary conditions to it. So now we can probably erase this, okay, and then substitute this into here, W1, W2, and then we get del prime equals to W1. And then, oh, that's what we need to substitute here, such A sine A1 sine mg plus B1 cosine mg, okay, and then multiplied by cosine kx, and then plus W2, okay, is A2 sine mg plus B2 cosine mg times sine kx. Okay. And so now, because we're sine, or cosine, or cosine, cosine, we're sine, sine, cosine, cosine. So we can apply the trigonometry, okay, trigonometry relationship, okay, to reorganize. And then we reorganize and use a different set of coefficients, C, D, E, F. Okay, we can substitute and then reorganize, we become like this. So this can be reorganized using the relationship. Okay, so then we get del prime of xg equals to C cosine of kx minus plus mg kx plus mg, and then plus d, and then sine of kx plus mg, and then plus e, and cosine kx minus mg, and then plus f sine of kx minus mg. Okay, this is 5.1.28. Okay, everybody follows me? Okay, that's good. Okay, so, okay, in 5.1.28, we have two types of waves. One is cosine x plus mg, another one is, okay, another one is kx minus mg. Okay, so before we talk about physical meanings, Let's just look at mathematical meanings of those. What do they mean? So we have two types of waves, right? One is kx plus mg. Okay. Another type is this one type. Another type is kx minus mg. So mathematically, what do they mean? Mathematically, if say I have a mountain here, like this, and if say I look at this term, what does that mean? Cosine kx plus mg. Okay, this is called phase. Okay, this is gives the phase. Okay, and if you have you have the coefficient here. That's called amplitude, and this is phase. Okay, so now if we look at the constant phase, okay, constant phase could be like you have a wave. Okay, you can look at peak. That's constant phase. Or you can look at the valley or anywhere you want, as long as it's at a certain point, which is consistent everywhere. So you look at here. Okay, and remember in pure gravity waves, okay, we have one wave, go like this. This is called phase tilt. You look at the peak of the wave, you follow it, okay, going up, you follow it, that's tilted against the flow, that's called, okay, this U, upstream phase tilting. Phase tilt. And so these two waves, one is tilted upstream, other one is with height. Okay, with height. So this is height, and this is extension, and other wave is tilted downstream. So first tilted downstream. So this is called downstream phase tilt. Okay, again, you can look at any point you want. So say if we look at the wave peak, the peak of the wave, okay. And this is tilted in the same direction as U, so that's called downstream phase tilt. This upstream phase tilt against the flow. Okay, this here. Okay, now if we look at say cosine of kx plus mg. The question is, this one give this tilt or give this tilt? Upstream. Okay, so upstream. Everybody agrees with her? How many people agree with her? No, very good. How many people don't agree with her? No, that's very good. Okay, you're very supportive. Okay, so now you support her, right? So can you explain why? Or maybe you can explain. Can you want to come here? Yeah. Yeah. Yeah, give it a try. Yeah. Yeah, give it a try. Over there. Use different color probably. Yeah.
I think if I focus on x and z, if k and n is constant and x and z. So
They were.
if I decrease, if this is constant, x is decreased and z should be increased.
Very good. Very good. Okay, so I think what she is trying to say is this. So say if, because it's any phase, you can look at peak or bottom, doesn't matter. So say if we look at the phase, constant phase, say we just make it equal 0, that, okay, that particular phase. Then kx plus mg equals to 0. Then that means g will be equals to negative. Okay, maybe I just simply do this. Okay, so now if, okay, if I, okay, go by x, then the g will be negative, right? If I go downstream by certain distance, okay, so if I go downstream by certain distance, so say this is x, then, okay, I increase this. In order to be 0, g got to be decreased. Right, agree? Okay, so that means your g is going to decrease. G decrease. So then it's going to tilt this way. Okay, if we look at kx plus mg equal 0, if negative here, that's another type of wave here. Okay, then that means if we increase x, that's we come downstream, and then g is going to have to increase too. Agree? Okay, so let's increase here. So get this. So then this is this one. Okay, so this one is km minus mg, okay, equal 0. That's cosine of kx minus mg over sine. Okay, and this one is kx plus mg equals to 0. So if x increase, then okay, g is going to decrease. So this type of wave, okay, is cosine of kx plus mg, like that. Okay, and actually you can calculate this type of wave will give upward energy propagation. This is downward propagation. Okay, you can do that using the, I think using probably that the vertical flux of the horizontal momentum. Then you can calculate it. Okay, and or energy propagation. Okay, you can calculate that. And this is similar to what we had before. Remember, in the beginning of doing this, I said you can have you can use this WGG plus m square w equals 0, and w you can write as a e to the I mg plus b times e to the minus mg. Remember that? And this one is upward propagating, this downward propagating. Okay. Yeah, so similar argument. Okay, here we just use the normal mode approach, and right now we use a simple mountain, so we do this. Okay, so what does that mean? That means this is upward propagating wave, this downward propagating wave of the wave energy. So then okay, so it can be shown that terms of kx plus mg has a positive vertical energy flux. Okay, so we have to retain them. We have to keep them. Okay, this. Okay, this. Okay, so see here, this Kx plus mg, this positive mg, that's similar to, I just erase it, okay. That is upward propagating wave, this downward propagating wave. Oh, I erase it. Okay, I erase it. Okay, so here, that gives us W1 equals to A e to the A1 e to the I mg plus B1 e to the minus I mg. This is upward, this is downward propagating. So this corresponding to this, okay, this plus 1, upward. This one, negative, is corresponding to this negative mg. Okay, so you can use either approach, but right now we use this one because our mountain is sinusoidal. That's why. Okay, so that means we have to keep this because our energy source is at the bottom. So our energy got to go up. So we have to keep this upward propagating wave, this part. Chia Hong, write down. Okay, so that's a good homework problem. Okay, to show, okay, the term with Kx mass mg is downward propagating wave of the energy, and this one is upward. Okay. Okay, so this is called the Sommerfeld radiation boundary condition. Okay, and Sommerfeld radiation boundary condition is like when you have the source of the energy, then the energy is going to associate with the disturbance, going to propagate away from the source. So say, for example, if you have the mountain here, okay, and wave generated, it's going to propagate away from it. Okay, and right now away, only way is up because no boundary you cannot penetrate, so only way is going up. So say if you play the drum, you know drum, pago, dagu, okay, you play it, and then your disturbance is in the middle, and wave will propagate out. That's called radiation boundary condition. Or you throw, okay, maybe you got mad, okay. Dr. Lin gave us too much homework. Okay, sorry, I don't like it. Okay, and then drop into the palm, okay, in the pond or lake, and then that's your disturbance center. Then the wave energy is propagating, wave is going out. Okay, that's called radiation boundary condition, Sommerfeld radiation boundary condition. Okay, and he has a very thorough discussion in his 1949 book. Okay, so in that case, we have to drop which terms? Which terms we have to drop? Speak out. Speak up. So which term we should drop? E and F. Okay, E and F. Okay, we drop. So then we only have C and D, two coefficients. And then we will apply the lower boundary condition and upper boundary condition, okay, to solve it. Okay, so we already applied the upper boundary condition now, right? It's radiation boundary condition, upper boundary condition, radiation. And so this is useful. Why not? Why? Because sometimes you maybe feel like a little bit intense and difficult to understand, but once you understand it, then later when you are learning or running the Wolf model, then you look at the upper boundary condition, they have, okay, radiation boundary condition. Okay, that's the same concept. Okay, so you have energy produced within your model domain, okay, had to be advected out. Otherwise, if wave energy coming back, okay, artificially from your upper boundary conditions, then that's not right. Okay, of course, if you have internal boundary reflect back, that's okay. But if it's okay at the top of the your model domain, and you don't allow energy propagate out, then you have artificially reflected back of the wave energy. That will contaminate your solution. And your solution still probably look beautiful, okay? But it could be wrong or kind of not quite correct. Okay, so then in next hour, we are going to talk about apply the boundary condition, lower boundary condition to it, okay? And then solve it. And then we can explain all those distributions of different fields, W prime, theta, U prime, P prime, theta prime, okay? And their behavior, its behavior is very different from the evolution flow, okay? And this is called vertical propagating wave, and their distribution of those fields are totally different, okay? Okay, so let's take 10 minutes break. And so, see you later. Thanks. Okay, so we'll start to apply the low boundary condition, and okay, we already apply upper boundary condition already. So we'll try that. So let's erase this. Okay, so that means W prime is equals to C times cosine of Kx plus mg. Okay, and then plus D, and then sine of Kx plus mg. C and D. Okay. Okay, this is low boundary condition. Okay, so this gives us W prime equals to U times partial x of Hm sine Kx. Okay, that's, we substitute this. Okay, this H into here, okay. And then that gives us Hm is constant, so we pull it out, okay. And then ddx of sine Kx will be K times cosine, right? So the K cosine Kx, okay. So this is low boundary condition. W prime is this low boundary condition. Okay, so this is our W prime, and this is our lower boundary condition. This is our solution, our boundary condition. This is in general that can apply to any x and g. This one is only at g equals to 0. So when you apply this low boundary condition to this, we have to look at g equals 0. Okay. So at g equals to 0, this means W prime equals to, any question? Equals to C cosine and Kx plus D sine of Kx, right? So these two solutions had to be equal, These two has to be equal. So the only way it can be equal is t equals to 0. Okay, because sine and cosine are orthogonal functions. Okay, so only thing this compare these two. Only thing is, okay, this implies t equals to 0, and cosine term, the coefficient of the cosine term had to be equal. So this means c had to be equals to u times hm times k. Okay, so identical to 5.1.29, like this. So this means, okay, this means our t equals 0. So our solution will look like this one. Okay, this one. So t term is gone. C is equals to UHM. So we apply this to here. That gives us W prime equals to UHM times K, and then cosine of Kx plus Mg. Okay, that's the solution. Okay, and this solution will give us upstream propagating wave, the first tilted upstream with height. Okay, and then you also can calculate the eta. Okay, and this. Yeah. Okay. Yeah, this is a good problem for them to do. Okay. Yeah. Okay. Yeah, the 5.1.31 to 34. Okay. So now, based on the eta, okay, definition, W prime is equals to U partial eta partial x, and you can derive that. And U prime, you can derive from the continuity equation. And then P prime can be derived from U, okay, and the Bernoulli equation, that is horizontal momentum equation in x direction. And then theta, you can do it, same thing. Okay, you can get this. And then once you get this, we got a complete solution, okay, in every variable, and that will help us to understand the wave behavior. Okay, so then it's like this one in B. Okay, and one thing very interesting is once you get that, you can plot it. You can plot it, and then you find your coldest region still on peak of the mountain, valley of the mountain, peak of the mountain. That makes sense, right? No matter what. Okay, you bring air up, okay, it's going to be getting colder, okay, by adiabatic expansion. And then you bring down, will be warm, okay, warm. Okay, so, and now this U prime will be negative now. Before, okay, before our U negative is here, our U negative is here, but now U prime is negative here, okay, and U prime is negative here. Before, remember, we have, okay, okay, look at above here. Let me see, okay, in order to have people online to see, so let me use the mouse. So here, you see here, we have cold air here, we have cold air here. Warm air here, warm air here. That can be explained no matter what. Okay, bring air up, it's going to cool down. And then bring down, it's going to open up. So we still have that. The coldest region on top of the mountain. Okay, warmest region on bottom. However, U prime, maximum U prime, very strong wind, because of that, okay, is no longer there. It's here. Okay, because here is narrowest region. Okay, and you have strong U prime here. And here is widened up over the upslope. And here is widened up over the valley. So U prime is negative here, minimum U prime. Okay, and then maximum U prime here over the mountain top. But here U prime is strongest on downslope. So when your wave generated, then your strongest wind is downslope and weakest here because here widen up. Okay, here narrow down here, and if in a different flow regime, it's over there. Okay, over the mountain peak. Okay, so and then the W. Okay, W is strongest here, and then strongest here. Okay, this upslope. Okay, strongest here is minimum because downslope very strong downslope wind here. And pressure is just opposite to the U prime. Okay, pressure. So here U prime is negative. That's okay. Wind is slowest here, and then you got highest pressure, and here lowest pressure. Okay, so now one more thing is now you can see. Can you see there's a mountain drag? Can you see? See here? Okay, because of tilting, so you have high pressure built up here, the low pressure here. So if pressure force acting on the mountain, okay, and that because of that acting, that gives the wave energy propagate upward. And you can calculate the D, the mountain drag by this, or momentum flux by this one. You'll find you can drag. Before there's no drag, now you have drag here. Okay, the mountain drag here. Okay, so the positive wave drag on the mountain is produced by high pressure. Okay, on the windward side, that upstream, okay, slope, upslope, and low pressure under this slope, that's here. As I just mentioned, high pressure here, upslope, and low pressure under this slope. So then you have mountain drag, you have pressure force difference like this. Okay. Okay. Here also, like before, like chapter 4, in the pure greater waves, if we have this L square greater than K square, but much greater, that means the equation will become the following. Okay, so we have the square W prime dx square plus the square W prime dg square and plus L square W prime equals 0. Okay, this one is n square over u square. Okay, just ignore the wind shear term, and this is constant. So this one is dominative. Okay, and this will give us Wi, okay, Gg plus Wi, Xx, let me see, plus L square minus K square, and then Wi. Okay, maybe I just use 1. Okay, I just use 1 equals 0. We have two equations, W2 Gg plus L square minus K square, and then W2 equals 0. Okay, so look at this. Now, for this extreme case, we have L square much greater than K square. That means compared to L square, this can be ignored, this can be ignored. So equation becomes simpler. We have W1 Gg plus L square, W1 equals 0, and then W2 Gg plus L square, and W2 equals 0. Okay, and this, okay, this means it's in hydrostatic balance. Okay, I think in one of the homeworks, I ask you to trace back. Okay, trace back, you'll find this term is related to the acceleration term, vertical acceleration. That term, okay, can be ignored because this term is corresponding to we have the p prime, the g equals to negative rho g. Okay. Yeah, we got rho g like this. Okay, so probably we have we probably have g and then theta prime over theta naught. Okay, so this term is corresponding to, and then I think let me see. Probably let me write the whole equation here. So we have partial W prime, partial t. Okay, plus u, partial prime, partial x, and then equals to negative 1 over rho naught dp. Negative theta prime, theta naught times g, and then negative dp prime dg like this. Okay, yeah. So this term is corresponding to, okay, it's steady state. So this term is corresponding to this term here, acceleration, vertical acceleration. So if it's in hydrostatic balance, this term is gone. Okay, so then you have vertical pressure gradient force, okay, balanced by the buoyancy force. Okay, so this is buoyancy force. This is pressure gradient force in balance. That's hydrostatic. This is corresponding to vertical acceleration. Okay, like this one, because it's steady state. So vertical acceleration is associated with u d w prime dx. Okay, you can trace back. It's one of the homework problems. Okay. So now this is summary. When L is less than K, okay, L is less than K, we have the evanescent flow. Yeah, any question? Any question? Yeah. Yeah. You keep talking, I'll split you guys. Okay. Yeah. You have to sit over there. Okay, so now if L square is much less than K, then we have the irrotational or potential flow. Okay. And if L greater than K, then we have vertically propagating wave. And then this whole thing on the right hand side is vertical propagating wave, but extreme case is hydrostatic waves. By the way, you have a question about that 5.1.20. Okay, so when I talk about those integrations, okay, like eta, okay, and like pressure, okay, like E prime, like theta prime. Those integrations are supposed to be from zero, okay, to x, okay, 0 to x. Because this is sinusoidal, you have to choose one point. If it is isolated mountain, then you can choose negative infinity. Okay, so you just have to correct it, my naught, okay, to be 0 here. Okay, so can you send me email? Okay, so I can, correct the modify the naught. Okay, good. So good news, we finished 7.1 and 7.2. Okay, it's not easy. That is a core problem to explain to people. Once you go through that, this one will become relatively easier. You just have more complicated mathematical manipulation because it's isolated mountain. And isolated mountain is, okay, different from the sinusoidal mountain. In a way, it's theoretically dynamics are the same. But difficulty is when you have the sinusoidal mountain, then you can just use the sine, cosine, okay, and you can easily, okay, derive it. But that's limited for only one wavelength, But in reality, it is composed by different wavelengths, okay, all the waves, and that we have many different Ks, different K. K will not be constant now, okay. So that's the situation here. It's two-dimensional uniform flow over isolated mountains, isolated mesoscale mountains. I put the mesoscale here is because we are going to ignore rotation again. And uniform means U is constant, like, okay, section 7.1 and 7.2. Okay, so here we are going to apply the Fourier transform, okay. And normally Fourier transform is going from, okay, you don't go like this way, okay. You don't take this rear part, okay. You regular Fourier transform. There are many ways you can define, probably 2 or 3 ways you can define Fourier transform, okay. And the regular one is when you have a function of x, then the Fourier transform into the Fourier space, this real space, or physical space. This Fourier space. So why we worry about this Fourier space? Because our mountain now is isolated like this, okay, and this is equals to, you have wave like this with, okay, mountain like this, and plus shorter wavelength of the mountain, plus even shorter, plus even shorter mountains, kind of infinite number of waves with different wavelengths add together to this first, okay, this isolated mountain. So now your K is no longer constant. So it becomes complicated. So you cannot apply method of normal mode, because method of normal mode you assume only one K. K is constant, only one, okay, K. But here we have many Ks, many K. So we have to use Fourier transform. And the regular way is probably, I believe all of you have learned from the mathematics, okay. So normally what we do is, so say you have x here, f of x, then you transform, we call Fourier transform, okay. This means transform, Fourier transform, to f of k, okay, equals to 1 over 2 pi. Okay, you have negative to positive infinity, and then you have f of x, and then e to the ikx, and then dx. Okay, it's negative. Okay, some people use positive too. Okay, so negative, and then when you transform back, you have fk, you transform back, so you have f hat of k. You transform back, then you can get x, f of x, okay? And then that's equals to negative infinity to positive infinity, and then f of k, okay, e to the ikx dk, okay? So, and some people use probably this, and then, okay, 1 over 2 pi here, and then some people use this positive, use negative, doesn't matter. As long as you you have f, you make Fourier transform, you give a specific function. You make Fourier transform, and you plug in here, coming back, you get the same function. No matter how do you define it, you can do that. So now we use a little bit different Fourier transform. We just use one-sided. This was proposed by Kane et al. 1960. Kane is a kind of very well-known mountain meteorologist, atmospheric scientist, but he specialized in mountain waves. So he defined this way. He defined when you come back, you go forward. This is called forward transform. This is called inverse Fourier transform. Inverse. Inverse Fourier transform. You transform back, then you transform back. You use f of x equals to 2 times real part. And then you integrate from 0 to infinity of f hat of k, and then e to the minus e to the plus ikx. So we don't need to say plus here, and then dk. So if we use these two, that's called one-sided Fourier transform. You can still apply the regular Fourier transform, but just it's more convenient in a way. And when this happens, this can be done is because convenience is k is always positive here. So you just use positive k. So to do this, and this works also very good for symmetric function. Then you do that. So now we are dealing with same problem. The governing equation is same. And then L square again is n squared over u squared minus ugg divided by u. And now we make Fourier transform. And you'll find out it's the same as before. Amazing, right? And no surprise, because for each k, you got same solution. So for all of them will be same. Governing equation. So now we have this partial square w prime partial x square plus partial square w prime partial g square, and then plus L square of g, and then w prime equals to 0. So when you make the Fourier transform, when you make a Fourier transform, we do this because now the k is no longer constant. So what you do is you make a Fourier transform of this equation. Then you have to apply for term w prime dg square. For this term. For this term. Then that that becomes we have negative to positive infinity Okay, and then of 1 over 2 pi, and then we have d square, w prime, dg square, and then e to the minus ik x dx. That's a Fourier transform of this term. Okay, so this is the Fourier transform. We want to do Fourier transform for the whole equation, so we do this. All right. So this is the simplest term. Why? Because partial g is nothing to do with dx integration. So we can pull that out. That becomes 1 over 2 pi partial g square, and then integration of w prime e to the minus ik x dx. Okay, so what's this? This is equals to, actually we can swap them. This equals to partial square, partial g square. Okay, and then 1 over 2 pi, like this. We can do this, right? Because ddg is nothing to do with dx, so you can pull out of the integration. And 1 over 2 pi is constant. You just pull into here. What's this? W head of k. Okay, so that means this auto transform will become d square w head dg square. Okay, so d square w prime dg square, the Fourier transform will become like this. Okay, and so say term 1, term 2, term 3. So this term 2, okay, become this. And term 3 is you have L square of g and w prime, and then you make a Fourier transform. Then that gives us what? 1 over 2 pi, okay, negative to positive infinity times L square of g and w prime e to the minus ikx dx. Again, same thing, this is constant. We pull out to here. So this gives us L square of g, and then 1 over 2 pi, integrate from negative to positive infinity, and then w prime e to the minus ikx dx. What's this? W head. Let's call head. Okay, W head. Okay, it's called W head. Okay, this okay, head. Okay, so then this is L square times W head. Okay, so that means this L square W prime, the Fourier transform will become L square W head. So that's pretty simple. The problem is this one. Okay. So problem is first term, the square, W prime, the S square, the Fourier transform. Okay. So the Fourier transform is again same thing, right? We just apply to 1 over 2 pi, integrate from negative to positive infinity, and then the square W prime, the S square, and then e to the minus ikx, and then dx, like that. Okay. So to do this, you have to, because it is isolated mountain, so now for infinity you can assume W prime equals 0. Okay, and then you have to do this by which kind of method? When you do integration? By parts. Okay, by parts. You can integrate by parts, like you have u dv, that would be uv minus v du. Okay, and you can do twice, and that will give you the answer. The answer is going to give us the square. It gives us negative k squared, and then w hat. So it's very similar to ddx, will be corresponding to ik, like normal mode approach or method or normal mode would be like this. Okay, and you can figure it out. Okay, I don't think I have time to do this for you. Okay, maybe homework. I'm going to scare them to death. Okay. Whenever there's a tough problem, okay, that's homework. Okay. Okay. So now, okay. So now we'll correct all those terms. Okay, so this equation. Okay, after Fourier transform, we have negative k squared w hat plus d square w hat dg square, and then plus l square w hat equals 0. And then you pull these two terms together. That gives us d square w hat dg square. Okay, plus l square minus k square, and then w hat equals to 0. Same equation. Okay, as the normal mode or sinusoid mountain. Okay, but here we can allow the isolated mountain. Okay, so but the governing equation is the same. The tricky thing is when you transform back, inverse Fourier transform, sometimes it's become very sticky, very difficult to do. Okay. Okay, everybody got that, right? Yeah. Yes. Okay, so now, since it's isolated mountain, so then we are going to apply Fourier transform. And the governing equation will become same as before. Equals to 0. Okay, the governing equation. And then upper boundary condition, because we have second order differential equation, that will require two boundary conditions to solve it. And again, upper boundary condition. And upper boundary condition will be same as before. It depends on flow regimes. Different flow regimes have different boundary conditions. One is upstream propagating wave. Another one is evanescent, same thing. Okay, so now we build up one by one step. So each time we add little bit complication. We add more complication. So that one now you totally understand that part, but just have to treat the complication part. Right now, complication is because now k is no longer constant. Okay, it's a combination of many numbers, actually infinite number of wave numbers. And then the kind of tricky thing here is you have to make Fourier transform back. Okay, lower boundary condition, same as before. Okay, so free slip. So then we have w prime equals to u partial x at g equals to 0. Okay, and now this tricky thing is here. Okay, so now we wanted to isolate the mountain. So we also assume, okay, we assume the bear-shaped function or bear-shaped mountain. Okay, so then if we have a mountain like this, bear-shaped, then our h of x is equals to hm divided by x squared plus a squared and times a squared. So when a is equal to 0, okay, x equals 0, then we have x equals 0. What's this? hm. That's mountain height. And how about when x equals to positive and negative a? We have a here, we have a here. So this is a squared, then that is half of the mountain. Okay, half of the mountain. So probably here, probably here. Okay, so this will be negative a, will be positive a, x. Okay, x equals to negative a. And that's, this a is called half width. Because, okay, at a, no matter it's positive or negative, okay, then this becomes a squared, then becomes hm over 2. That's half of the mountain height. Okay, so this mountain height, okay, at a, will be half of the mountain, hm over 2 here, hm over 2 here. Okay, and that's called the half width. Okay, and so tricky thing is now, once you have this, okay, then we have to make the Fourier transform so we can apply in the free space, because it's in the free space here, and here is a real space. Okay, so here you can make the Fourier transform, okay, and that become W hat of, okay, again, partial x corresponding to ik. Okay, you can easily prove it, okay, when you do Fourier transform of partial derivative with respect to x. And then that will give us ik times u, okay, and then h hat of k. Okay, now once you have this, then we also have to apply there, right? We have to make Fourier transform. So we have to get h hat of k. So h hat of k will be equals to what? 1 over 2 pi negative infinity to positive infinity of hm a squared divided by x squared plus a squared, and then e to the minus ikx dx. Okay, and this one, you can do it. Yeah, homework. Okay, so you can do it. Okay, and that's the neat, the beauty of this function. And this function, this bear-shaped function, was proposed by a French female scientist, mathematician. And so, okay. Okay, so, okay, this is called the bear-shaped mountain, or the which of accuracy mountain profile, okay, or which of accuracy function, and which, you know which, right? Okay, 物思, right? Okay, and accuracy is that French female mathematician. Okay, so if you Google search, you can find that. Okay, like this. So HM is mountain height, A is head width. Okay, because the mountain height at there is HM divided by 2. Okay, and so go back here. So since we have this governing equation, and then our solution actually, okay, well, again we assume constant scalar parameter. That means we assume there's no vertical wind shear. Okay, it's uniform flow. And then equation solution will be a little bit different from before because K is not constant. K is not constant. So you have many Ks, many K, they are different. And some K, in the same solution, some K is greater than L, some K is smaller than L. So then you have to make it continuous. Okay, and that is why we have this part. Okay, if L square is greater than K square, then we have W head equals to W head K 0. Okay, this is low boundary condition determined by low boundary condition. This low boundary condition, and then here you I square root. Remember, IMG is negative. Okay, negative lambda g. Remember that. Okay, so here L square is greater than K square. Here K square is less than L square. L square is less than K square. So then you have two solutions together. Okay, because some waves will have wave number less than L square. Some wave will have wave number greater than L square. So this is for longer waves and shorter waves. And then you have longer waves, shorter waves all combined together. So you have this little bit complicated mathematically. Okay, but physically it's not that complicated. Okay, and then once you have this, then we have to take the inverse Fourier transform, one-sided. Okay, you take 0 to L because here K must be less than L. So only K only go from 0 to L when you do integration, and here K will be greater than L. The solution will be different from this. Okay, for this case, K is less than L because K has to integrate from 0 to K equals to L. So K must be less than L. So that will be this solution. And the second part will be different. So I combined the vertical propagation waves, some of them, and some of them are evanescent flow, and combined together. So solution become complicated because you have two parts. Okay, one for smaller K, that's longer waves, and here is larger K because K is greater than L. And this is for evanescent flow. Okay, combined together. So you have to solve this, and first you have to solve this H head of the which of accuracy. That's the this bear-shaped mountain. You have to transform that into Fourier space. Okay, so we have to do this, and that homework, right? Okay, we agreed. Okay, so yeah, so but don't overlook that solution. It's very complicated. Actually, in general, you cannot solve it. In general, you cannot solve it analytically. So, okay, congratulations. Okay, I'm not going to require you to solve that. Okay, overall, because you cannot solve it. Okay. Yeah, you cannot solve it. You only solve on extreme case. One is L square much less than K square. And other one is L square much greater than K square. And then other one is L square is about same as K square, approximately equal. And then you can use asymptotic solution approach to solve this solution. Okay, so Again, congratulations. Okay, I will not ask you to solve this. Okay, we will solve together here. Okay, and I'm not asking you to solve general solution there. You can actually, you are good. You can do it using numerical method. Okay, that's called fast Fourier transform, FFT. And FFT is interesting, has a very interesting history, because let me talk about this joke. This is not real joke, this is real story. And then we can go home, okay? So that you feel better. The Fourier transform, first Fourier transform was developed by accident, because there's a mathematician, and he always, but he's a mathematician. He's not a programmer. He doesn't know much about program. He's just some basic Fortran or whatever. And so he always wanted to do this Fourier transform back. Okay, Fourier transform one way is okay, but forward is okay, but backward, inverse Fourier transform is always difficult. So he always wanted to help to find a solution to do it, okay, numerical solution. So then one day he went to have lunch with his friend in IBM research lab. Okay, IBM used to have a big research lab and have top scientists there. So he talked with his friend. His friend is a mathematician too, but more numerical type. And he asked, "Do you have somebody can help to develop, to write a Fortran code to numerically integrate that Fourier transform, inverse Fourier transform?" And his friend said, looks like it shouldn't be that difficult. Let me try to go back and find somebody who doesn't have important things to do.